The farthest thing you can see with your naked eye is about 2.5 million light years away. That's Andromeda, a whole galaxy 2.5 million light years out, visible without any equipment on a clear night. It sounds impossibly far. It isn't even close to the edge. The observable universe stretches 45 billion light years in every direction. The universe itself is only 13.8 billion years old. Those two numbers should not be able to coexist. Something has to be wrong. The light should not have had time to travel that far. Physics has a speed limit, and everything you've ever been told says nothing breaks it. And yet the universe is 4 times wider than light could have traveled since the beginning of time. That is the first thing to hold in your mind before anything else. The numbers don't add up, not even close. Here is what makes it stranger. You can see galaxies sitting 13 billion light years away. You can photograph them, name them, measure their temperature, and you will never reach them. Not you, not your descendants, not any ship built from any material, running on any fuel, pointed in any direction. Those galaxies are gone, already beyond reach, permanently. The light you're receiving from them is 13 billion years old, which means it left when those galaxies were nowhere near where they are now. Where they are now is somewhere you cannot go, cannot signal, cannot touch in any way. You are looking at a ghost and calling it a neighbor. Most of the observable universe is already in this category, not someday, now. 94% of everything we can see sits beyond a boundary that nothing we send out will ever cross. Every year, roughly 160 billion stars slip past that line and leave our reach forever, quietly, without any event you could observe or mark on a calendar. The universe is shedding territory we never knew we had, and the loss is permanent. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. None of this is a failure of engineering. No faster engine fixes it. No better telescope recovers what's gone. The problem is not the speed limit. The problem is something running underneath the speed limit. Something happening at a level that makes the speed limit irrelevant. The reason involves something that has nothing to do with how fast you go, and everything to do with what space itself is doing underneath your feet. When you look up at a star, you are not looking at the present. You are looking at a photograph, a very old photograph, taken at a moment that may be thousands or millions or billions of years gone, still traveling toward you at the speed of light, arriving only now. The star you see tonight is not the star that exists tonight. It is the star that existed when that light began its journey, and depending on which star you're looking at, that journey may have started before humans existed at all. Start with the closest example. Proxima Centauri, the nearest star beyond our own sun, sits about 4.2 light years away. The light hitting your eyes from that star left it roughly 4 years ago. That is almost nothing by cosmic standards. 4 years is recent. 4 years ago you probably remember what you were doing. But even that modest delay means you are not seeing Proxima Centauri as it is right now. You are seeing a version of it that is already history. If something catastrophic happened to that star this morning, you would not know for 4 more years. The information cannot travel faster than the light carrying it. Scale up slightly. Betelgeuse, that red restless star sitting on the shoulder of Orion, is roughly 650 light years away. The light you see from Betelgeuse tonight left that star around the year 1375. Knights were riding through Europe. The Black Death had just swept the continent. That ancient light has been crossing empty space ever since, and it only just arrived. Whatever Betelgeuse looks like right now, in the actual present, you have no way of knowing. The star could have already exploded. It could have collapsed. Something vast and final could have happened to it centuries ago, and the news is still in transit. For all the telescopes and instruments trained on that corner of Orion, every single observation is still looking backwards. This is not a minor technical footnote. It is the fundamental nature of all astronomy. There is no such thing as observing the universe as it currently is. Every observation is an observation of the past. The only question is how far back you are looking. Move farther out. The Andromeda Galaxy hangs in the northern sky, faintly visible to the naked eye on a clear night, a smudged oval of ancient light. That light left Andromeda approximately 2.5 million years ago. At that time, the genus Homo had barely appeared on Earth. Stone tools were new. Fire was still something humans found rather than made. The photons arriving at your eye from Andromeda were already in transit before any human being had ever looked up at a sky. They have been crossing intergalactic space ever since, now pushed to the edge of what our best instruments can see. The James Webb Space Telescope has detected galaxies whose light originated only a few 100 million years after the Big Bang. The most distant confirmed galaxy detected as of the past year, a galaxy called month-over-month Z14, shows us light that left its source just 280 million years after the universe began. That light has been travelling for approximately 13.5 billion years to reach us. The universe itself is only 13.8 billion years old. What we are seeing in that image is the universe in early infancy, galaxy formation happening in real time, structures coalescing from gas clouds in a cosmos that barely existed. And we are seeing it now, tonight, with instruments parked in space above Earth's atmosphere, because those photons finally finished their journey. But the galaxy that emitted that light, that galaxy has had 13.5 billion years to change. It is not the same object anymore. It has merged, evolved, possibly been torn apart and reformed entirely. We are looking at something that no longer exists in the form we see it. This is what makes the night sky genuinely strange once you sit with it. It is not a window. A window shows you what is happening right now on the other side of the glass. The sky is something different. The sky is a museum. Every object in it is on display at a different point in its history. The star 4 light years away is on display from 4 years ago. The galaxy 2.5 million light years away is on display from 2.5 million years ago. The farthest objects our telescopes can resolve are on display from a time before Earth existed, before the sun ignited, before our entire solar system had formed out of gas and dust. We are surrounded on all sides by exhibits, each one frozen at a different moment, each one sending us a message dispatched long before the message arrived. Some of those objects no longer exist. The star you are looking at might have already died. The galaxy at the edge of our observation might have collided with a neighbour 1 billion years ago and become something unrecognizable. There is no way to know. The light we receive is real. The history it describes is real. But the present state of whatever sent it is inaccessible to us, separated by the most reliable barrier in the universe. The simple fact that information cannot travel faster than the light that carries it. Every single point of light in the sky is a message from the past, and the past is the only version of the universe we will ever get to see. Here is the number that breaks people's intuition before anything else does. The universe is 13.8 billion years old. Light travels at 186,000 miles per second. So if you want to know how far light could have traveled since the beginning of everything, the math seems simple. Multiply the speed of light by the age of the universe and you get your answer. You'd expect the observable universe to be roughly 13.8 billion light years across. Maybe a little larger when you account for the light traveling in every direction from every point, but somewhere in that neighborhood. That's how rooms work. That's how any reasonable physical system should work. The edge of what you can see is determined by how far light could have traveled since the moment everything began. The observable universe is 93 billion light years across, not 13.8 billion, not 20 billion, not even 30 billion. 93 billion light years from one side to the other, stretching 46 billion light years in every direction from where you are standing right now. That number is not a rounding error. It is not a misprint. It is what every major telescope, every measurement of the cosmic microwave background, every careful application of our best cosmological models consistently returns. The universe you can observe is more than 6 times larger than the universe that simple arithmetic says should exist. Think about what that actually means. Imagine the Big Bang as someone switching on the lights in a dark room. The room was pitch black, then suddenly filled with energy, and that energy began spreading outward in every direction at the speed of light. After 13.8 billion years, you'd expect the light to have reached walls that are 13.8 billion light years away. That's just how light works. That's just how time works. But when astronomers look at the walls of this room, they find them 46 billion light years out, 4 times further than they should be. The lights have only been on for 13.8 billion years, and the room is already 93 billion light years wide. Something is deeply, profoundly wrong with the simple picture. Were the walls always that far away? Did the light somehow travel faster than it was supposed to? Is the universe older than we think? None of those explanations work cleanly. The age of the universe is one of the most carefully measured numbers in modern science. The speed of light is a constant. It doesn't change. It doesn't speed up in the early universe and slow down later. And yet here is this number, 93 billion light years, sitting in the middle of cosmology like a fact that refuses to apologize for itself. This is the moment where most explanations rush to rescue you with the answer. This one won't, not yet, because the confusion is actually important. You should sit with the feeling that something here is genuinely broken. The smartest instinct you have about how light and time and distance relate to each other is pointing you toward a universe that is 13.8 billion light years across, and that instinct is wrong by a factor of more than 6. That gap between your intuition and reality is not a small correction. It is not a rounding adjustment. It is the signature of something in the universe behaving in a way that has no equivalent in ordinary human experience. There is no analogy from daily life that makes this feel normal, because in daily life, nothing like this happens. What you are allowed to know at this point is that the explanation has nothing to do with how fast the galaxies moved. No galaxy raced across the universe at some impossible speed to reach its current position. No object broke the speed of light. Nothing in the history of the universe has ever moved faster than light through space. Every particle, every photon, every atom of hydrogen in every galaxy has obeyed Einstein's speed limit with complete faithfulness for 13.8 billion years. The problem is not that anything moved too fast. The problem is that the universe doesn't work the way a room works. A room has fixed walls. The distance between 2 points in a room stays constant unless something physically pushes those points apart. The universe does not have fixed walls. The universe does not have fixed anything. The fabric of space itself, the medium through which light travels, is not sitting still while light crosses it. It has been doing something else entirely, something that the simple multiplication of speed times time completely fails to capture, something that stretches the answer from 13.8 billion to 93 billion, and does so without violating a single physical law. That something is expansion, not the galaxies expanding outward through space like debris from an explosion. Not matter flying in every direction away from some central point. The space itself expanding, growing. The distance between every point in the universe increasing, not because things are moving through space, but because space itself is getting larger. And that distinction between things moving through space and space itself changing size is the hinge that the entire paradox swings on. The universe isn't bigger than its age because anything cheated. It's bigger than its age because the measuring tape itself has been stretching since the beginning. But none of this violates Einstein, which is either deeply reassuring or deeply unsettling depending on how much you were hoping for a simple answer. In 1929, an astronomer at the Mount Wilson Observatory in California looked at the light from distant galaxies and noticed something that would eventually rewrite every cosmology textbook on the planet. His name was Edwin Hubble, and what he found was not subtle. Before Hubble, the dominant picture of the universe was simple and deeply comforting. The universe was static. It had always been there. It would always be there, and the galaxies scattered across the sky were essentially fixed in place. Even Einstein, whose equations actually predicted a dynamic universe, had fudged his own math to force a static result. He introduced a fudge factor he called the cosmological constant, specifically to hold the universe still on paper. The idea of a universe that moved, that changed, that had a beginning, that was almost philosophically intolerable to most scientists of the era. The universe was eternal. Everyone agreed. Then Hubble looked at the spectra. When light passes through a prism, it splits into a rainbow, but embedded in that rainbow, at precise positions, are dark lines. These lines are the fingerprints of specific elements: hydrogen, helium, calcium, each absorbing light at exact, known wavelengths. Physicists had catalogued these fingerprints in laboratories on Earth. When you look at a star or a galaxy and break its light apart, you should see those same lines at those same positions. Hubble kept finding the lines in the wrong place, shifted, pushed toward the red end of the spectrum. And the fainter, more distant the galaxy, the more the lines had shifted. This is called redshift, and it meant one thing: those galaxies were moving away from Earth. On its own, that might not have been shocking, but Hubble went further. He plotted recession speed against distance for galaxy after galaxy. The relationship was not random, it was a straight line. Double the distance, double the speed, triple the distance, triple the speed. The farther a galaxy sat, the faster it was retreating, and the relationship was clean enough to be a law. We still call it Hubble's law. The rate, the exact speed per unit of distance, is called the Hubble constant, and current measurements put it at roughly 70 kilometers per second for every megaparsec of distance. 1 megaparsec is about 3.3 million light years. So a galaxy sitting 3.3 million light years away is receding at roughly 70 kilometers every second. A galaxy 10 times farther is receding 10 times faster. It scales perfectly. What does that tell you? It tells you the universe is expanding. But here is where intuition fails almost everyone the first time through. The natural response is to picture galaxies as objects hurling themselves away from us through empty space, like shrapnel from an explosion. We must be at the center, and everything is fleeing outward. That picture is wrong. It is wrong in a way that matters enormously. Think about a loaf of raisin bread rising in an oven. Before it goes in, the raisins are clustered at various distances from each other. As the dough rises, the bread expands in every direction. Now pick any raisin and watch from its perspective. Every other raisin is moving away from it. Raisins that started close are drifting apart slowly. Raisins that started farther away are separating faster, not because they're running harder through the dough, but because there is simply more dough expanding between them. Every raisin sees the same thing. Every raisin looks like the center. None of them are. That is exactly what Hubble was seeing. The galaxies were not racing through space. The space between them was growing. Every galaxy sees every other galaxy retreating, and the farther ones retreat faster, because there is more expanding space between them. There is no center. There is no edge. There is just fabric, stretching in every direction simultaneously. This distinction is not a technicality. It is the entire point. If galaxies were simply moving through space, Einstein's speed limit would cap them out. Nothing with mass can reach the speed of light. The recession velocities Hubble measured for the most distant galaxies already exceeded what any moving object should be capable of. But space itself is not an object. It is not made of mass. It has no speed limit imposed on it by relativity. Space can expand as fast as it wants, and nothing in physics says otherwise. This is why the universe can be 93 billion light years across after only 13.8 billion years. But space grew. The galaxies rode with it. Hubble handed this discovery to the scientific world in 1929. Einstein, to his considerable credit, visited the Mount Wilson Observatory, looked at the data, and publicly called his cosmological constant, the fudge factor he'd inserted to keep the universe static, the greatest mistake of his career. The static universe died in a single decade. What replaced it was stranger, vaster, and ultimately far more interesting. The galaxies were not moving through space away from us. Space itself was growing between us and them, and that single distinction is the key to everything that follows. To understand why light speed is not enough, you first have to understand what kind of thing light is actually moving through. Most people picture space as a stage, a fixed, empty arena where galaxies sit like actors, and light races between them across a floor that doesn't move. In this picture, Einstein's speed limit is simple. Nothing crosses that floor faster than 186,000 miles per second. Light is the fastest thing there is, so if you could match light speed, you could eventually reach anything. That picture is wrong, and the way it's wrong is the key to everything. Space is not a stage, it's more like a fabric, and that fabric stretches. This isn't a metaphor chosen for convenience, it is the literal physical description of what space does on the largest scales. The distance between 2 points in space can grow not because the points are moving through space toward each other's opposite ends, but because the space connecting them is actually expanding. The separation increases. The points themselves haven't gone anywhere. Here is the clearest way to see it. Take a rubber band. Draw 2 dots on it with a marker. Now stretch the band. The dots move apart, but neither dot moved relative to the rubber band under it. If a tiny ant sitting on one of those dots asked whether it had walked anywhere, the honest answer would be no. It stayed perfectly still, and yet the other dot is now farther away. The distance between them grew because the surface itself stretched, not because anything travelled across it. This is exactly what space does. Galaxies are the dots. The universe is the rubber band. Einstein's speed limit says nothing about how fast space can stretch. His equations govern objects moving through space. Ships, particles, photons, anything with a trajectory inside the fabric. The fabric itself is under no such restriction. It can expand at any rate the physics of the universe demands. In distant regions of the cosmos right now, space is expanding at rates far exceeding the speed of light, and no law of physics is being broken anywhere. No object is travelling faster than light. The space between objects is simply growing faster than light can cross it. This distinction matters more than almost anything else in cosmology. When astronomers say that distant galaxies are receding from us faster than light, they do not mean those galaxies are blasting through space like runaway rockets. They mean the space between us and those galaxies is stretching at a rate that, when you add it all up across billions of light years, results in a separation speed greater than 186,000 miles per second. Locally, in their own neighborhood, those galaxies are obeying every rule Einstein ever wrote. The violation, if you want to call it that, is happening in the fabric underneath them. Now put a photon in this picture. A photon leaves a distant galaxy heading toward us at the speed of light. That is the maximum speed anything can travel through space. Full stop. There is no faster option. But as that photon crosses the cosmos, the space it's crossing keeps expanding. Every second, new distance is being inserted into the gap the photon has to cover. The photon is moving forward at top speed, and the finish line is being pushed back in real time. Whether it ever arrives depends entirely on whether the expansion is outrunning it or falling behind it. For photons emitted from nearby galaxies, they win. Expansion is slow enough at those distances that the photon closes the gap and eventually reaches us. For photons emitted from very distant galaxies, it's a different story. The expansion rate at those distances is high enough that the gap grows faster than the photon can close it. The photon travels for 1 billion years, and the destination is still farther away than when it started. It will travel for another 1 billion years and gain no ground. It never arrives, not because it's slowed down, because the space it has yet to cross keeps being manufactured faster than it can consume it. This is the ant on the rubber band. Picture the ant on one dot, trying to walk to the other dot while someone stretches the rubber band at a steady rate. The ant is walking as fast as its legs will carry it. It doesn't stop. It doesn't slow down. It is putting in maximum effort at every moment. But if the band stretches fast enough, the destination dot moves away faster than the ant advances. The ant covers real ground. It is genuinely moving forward across the rubber band. And it still falls behind, because the total distance it needs to cross is growing faster than its walking speed can handle. A photon is the universe's fastest ant. Light speed is the fastest anything can move through space, and in enough of the universe, that is simply not fast enough, because the space being travelled through is expanding faster than the fastest traveller can cross it. There is no shortcut here. There is no engine modification, no theoretical loophole, no patience or ingenuity that changes the arithmetic. The expansion of space is not a barrier you push through. It is a property of the medium itself, and it scales with distance in a way that makes remote regions permanently inaccessible, regardless of how fast the traveller moves. The ant can run as fast as it physically can, and it still loses ground, because the thing it's running across is growing faster than the ant can run. At a certain distance from Earth, the recession speed of galaxies hits exactly the speed of light. Not because those galaxies are hurtling through space at some impossible velocity, but because there is enough expanding fabric between us and them that the cumulative stretching adds up to light speed. That boundary has a name. Astronomers call it the Hubble Sphere. Picture it as a vast bubble surrounding Earth, roughly 13 to 14 billion light years in radius in every direction. Everything inside that bubble is receding from us, slower than light. Everything outside it is receding faster than light. The boundary itself is the precise distance where recession speed equals exactly 300,000 kilometers per second. And here is the first strange thing about it. That boundary is not fixed. As the expansion of the universe accelerates, the Hubble sphere's edge shifts over time. Galaxies that are just inside it today may find themselves outside it in the future. This is not a wall drawn once and left alone. It is a moving threshold in a universe that refuses to hold still. Now, here is where most people's intuition breaks down completely. You might expect that the Hubble sphere represents the edge of what we can see. If a galaxy is receding faster than light, surely no light from it can ever reach us. That seems airtight. It is also wrong. Galaxies well outside the Hubble sphere are visible to our telescopes right now. The James Webb Space Telescope has photographed galaxies receding at several times the speed of light. We are looking at them. Their light is in our instruments. How is that possible? The answer requires holding two ideas at once. The Hubble sphere describes the recession speed of galaxies at this particular moment in the universe's history. But the light we receive from distant galaxies was not emitted at this particular moment. It was emitted billions of years ago, when those galaxies were much closer to us, when expansion was slower, and when some of those galaxies were still inside the Hubble sphere. That ancient light has spent billions of years crossing space, and during that crossing, conditions changed. The universe expanded around the photon while it travelled. In many cases, those photons started their journey in a region where expansion was slow enough that they could make progress toward us, and they have been gaining ground ever since, even as the galaxy that emitted them drifted further and further away. Think of it like sending a letter from a city that is moving away from you. The letter was mailed when the city was close. The city is now far, but the letter is already in transit, already moving towards you through a postal system that doesn't care where the city ended up. The letter still arrives. The city's current location is irrelevant to the letter already in flight. This is not a loophole or a technicality. It is fundamental to how the observable universe works. The light we receive is a record of the past, not a broadcast from the present. A galaxy sitting 30 billion light years away from us today, receding at multiple times the speed of light, can still be sending us photons that were launched when it was much closer and when the universe was expanding more slowly. Those photons have been making their way toward us for billions of years. They are still arriving. We can still see that galaxy. But the galaxy as it exists right now, the light it is emitting at this moment, is a completely different question. So the Hubble sphere is not the edge of the observable universe. The observable universe extends to about 46 billion light years in every direction, 3 times further than the Hubble sphere's radius. Everything we see beyond the Hubble sphere is ancient light from when those regions were closer. It is not current information. It is a fossil record encoded in photons. What then does the Hubble sphere actually tell you? It tells you where space is currently expanding at light speed. It tells you the rough dividing line between galaxies from which new light can, in principle, still make progress toward us, and galaxies from which the current rate of expansion is already outrunning any photon emitted today. But even that is more complicated than it sounds, because the Hubble sphere moves and expansion accelerates, and a photon emitted from just beyond the sphere might still reach us if it manages to enter a region of slower expansion before the universe drags it back. This is why cosmologists distinguish carefully between the Hubble sphere, the observable universe, and the cosmic event horizon. 3 different concepts, 3 different boundaries, all of them centered on Earth, all of them at different distances. The Hubble sphere sits at roughly 14 billion light years. The edge of the observable universe sits at 46 billion light years. The event horizon, the boundary beyond which no light emitted right now will ever reach us, sits somewhere around 16 billion light years. None of these numbers match. None of these lines sit on top of each other. Each one is measuring something different about the relationship between light, space, and time. The Hubble sphere tells you where space is currently expanding at light speed. It does not tell you the edge of what you can see, and it does not tell you the edge of what you can reach. And those 3 things turn out to be 3 very different boundaries. There is a boundary in space beyond which you could send a signal at the speed of light, and that signal would never arrive. Not in 1 billion years, not in 1 trillion, not if the universe lasted forever, which it won't. But even if it did, the signal would still never close the gap. This is the cosmic event horizon, and it is something categorically different from the Hubble sphere described in the last section. The Hubble sphere tells you where recession speed equals light speed right now. The event horizon tells you something far more permanent. It tells you the address of the last place in the universe that can ever hear from you again. The distance sits at roughly 16 billion light years. Any galaxy currently sitting beyond that line is already gone from you in a way that matters more than distance. It is gone from your future. Light that those galaxies are emitting right this moment, photons leaving their stars as you read this, will travel in our direction for the entire remaining life of the universe and never arrive. Space will expand faster than those photons can move, indefinitely, and the gap between them and us will grow for as long as there is a universe to grow in. That is not a poetic exaggeration. That is what the mathematics of expansion actually predicts. Here is where people get confused, and the confusion is understandable. If galaxies beyond 16 billion light years are truly unreachable, why can we see things that are 46 billion light years away? The James Webb Space Telescope is picking up light from galaxies near the edge of the observable universe. Those galaxies are far beyond the event horizon. How is any of that light getting here if the event horizon is a hard wall? The answer is that we are not seeing those galaxies as they are now. We are seeing them as they were billions of years ago, when they were much closer, when the expansion between us and them was much slower, when their light had a fighting chance of covering the distance. That ancient light has already arrived. It is already here. The event horizon doesn't erase the past, it only closes the future. Think of it this way. A galaxy 40 billion light years away right now sent us light 13 billion years ago. That light made it across because back then the universe was younger, smaller, and the expansion rate at that location hadn't yet tipped past the point of no return. The photons got a head start. They were already deep into the journey before expansion accelerated past them. But any photon that galaxy emits today starts from a position so far outside our reach that no head start is possible. It loses ground from the first moment it travels and never stops losing ground. The old light is a gift from a more connected past. The new light never gets to leave. This is the key distinction between the cosmic event horizon and the edge of the observable universe. The observable universe, stretching 46 billion light years in every direction, is defined by what light has already managed to reach us. It's a record of the past. The event horizon is defined by what can reach us in the future. Those are two entirely different questions, and the numbers that answer them are very different numbers. We can observe far beyond the event horizon. We simply cannot receive any new information from beyond it. We are watching a recording, not a live broadcast. Dark energy is what makes this wall permanent. Without accelerating expansion, the event horizon would be a softer boundary. Push hard enough with enough time, and photons from nearly any distance might eventually claw their way across. But dark energy changes the arithmetic. It doesn't just maintain the current expansion rate, it increases it. Space at large distances is expanding faster today than it was 1 billion years ago, and it will expand faster still 1 billion years from now. The event horizon isn't static. In a universe where expansion is accelerating, the window of what can ever reach us is gradually narrowing, not widening. Galaxies that sit close to the edge of reachability today will eventually cross to the wrong side of that line and go dark from our future forever. Even if their ancient light continues arriving for billions of years more, what makes this strange to hold in your mind is the asymmetry of it. We can still see these places. We can study them with Webb and measure their redshifts and deduce their compositions and estimate how many stars they contain. We are learning about things we will never contact. We are observers of a universe that has, in large part, already stopped being available to us. There is no fence, no visible edge, no point at which a traveler would notice crossing from the reachable side to the unreachable side. The boundary exists only in the calculus of expansion rates and cosmic time, real enough to be permanent, invisible enough to feel abstract right up until you do the math. The event horizon is not a place in space you could visit. It is a calculation, a line drawn by the mathematics of expansion, beyond which the future is permanently closed off. Say you had a ship that could travel at exactly the speed of light, and you pointed it at a galaxy sitting 20 billion light years away. You fire the engines. You hit maximum speed instantly, and then you watch the distance counter, waiting for it to tick down. It doesn't, at least not the way you'd expect. You're moving at the fastest speed anything in the universe can move, and yet the gap between you and that galaxy is growing. Not because your engines failed, not because you made a navigational error, Because the space between you and your destination is expanding while you cross it. Here is what actually happens when you do the math. In the time it takes you to cross 1 light year of distance, the universe is stretched. That galaxy is now slightly farther than it was when you started. You cover another light year. The galaxy recedes again. You are running on a treadmill that is accelerating. Your speed is constant. The treadmill keeps going faster, and unlike a real treadmill, there is no emergency stop cord. 20 billion light years is beyond the cosmic event horizon. That boundary sits at roughly 16 billion light years from Earth right now. Anything sitting beyond that distance is in territory where space is expanding faster than light can cross it. You already know from everything that's come before in this story that a signal sent from Earth toward that galaxy today will never arrive. But now think about what happens when you are the signal. You leave Earth at light speed. Let's say the galaxy is 20 billion light years away at departure. The Hubble constant tells us that space expands at roughly 70 kilometers per second for every megaparsec of distance. At 20 billion light years, the recession velocity of that galaxy is already well above the speed of light. So even as you travel at 300,000 kilometers per second through your local patch of space, the destination is retreating at a rate that exceeds what you're covering. You are gaining ground locally. You are losing ground cosmically. After 1 billion years of travel, you have crossed 1 billion light years. But the target has moved. Space has stretched the remaining distance significantly beyond what you started with. After 5 billion years, you've covered 5 billion light years. The galaxy is still not closer. It is further, not by a little, by billions of light years. The gap is widening even as you race toward it at the maximum speed the laws of physics permit. You are not slowing down. The universe is not slowing down. The universe is simply winning. This is the part that feels wrong. Intuition says that if you move towards something, you get closer to it. That's true when the thing between you and your target is static. When the thing between you and your target is space itself, and space is actively expanding, that intuition fails completely. You close the distance that already exists. Space creates new distance faster than you close the old stuff. The net result is a gap that grows no matter how fast you run. Think of it this way. Imagine you're trying to walk to the far end of an airport moving walkway, except the walkway is carrying you backwards at twice your walking speed. You walk. You put in real effort. You are genuinely moving forward relative to the floor under your feet. But the floor under your feet is moving backward faster than your legs can compensate. You will never reach the far end. Now imagine that walkway is accelerating. The longer you walk, the faster it carries you backwards. You started with no chance. Now you have even less. That is what dark energy does to this problem. The expansion isn't constant over time, it's accelerating. The further into the future you travel on your light speed journey, the faster the remaining distance grows. Each billion years of travel makes the problem worse, not better. Early in the journey, you might close some of the original distance before expansion overtakes you, but eventually, for any target beyond the event horizon, expansion pulls ahead permanently. There is no later moment when you catch up. The mathematics rules it out completely. And here is where it gets genuinely vertiginous. That galaxy at 20 billion light years is not hypothetical. There are real galaxies sitting at that distance right now, emitting real light. Some of that light has already reached us. ancient photons that left when the universe was young, and those galaxies were much closer. We can see them, we can study them, we can measure their composition, their age, the rate at which they're forming stars. We just cannot go there. We cannot send a probe there. We cannot send a message there that will ever arrive. Seeing and reaching are completely different things, and in this case they are separated by physics so fundamental that no civilization anywhere in the universe can bridge it. The answer is not a faster engine. The answer is not better fuel. There is no propulsion system, real or theoretical, that solves this problem, because the problem is not about propulsion. It is about the geometry of expanding space, and geometry does not negotiate. Maximum speed in a universe that is expanding faster than maximum speed is simply not enough, and there is no engineering solution to that problem. In 2024, astronomers using the James Webb Space Telescope announced a detection that rewrote the record books for the most distant object humanity has ever observed. The galaxy is called month over month Z14. It does not look like much in the raw data, a faint smear of light, barely distinguishable from noise. But the numbers behind that smear are staggering. The light arriving at Webb's mirrors today left its source just 280 million years after the Big Bang. The universe was not even 2% of its current age when that light began its journey. Stars were still figuring out how to exist, and somehow one of them managed to send us a message across 13.5 billion years of expanding space. Here is where the gut punch arrives. When that light left month over month Z14, the galaxy was relatively close by cosmological standards, roughly 2 billion light years away. Not nearby, but within a range that feels almost comprehensible. What happened between then and now is what makes this discovery so disorienting. Space expanded. It kept expanding. It expanded faster and faster as dark energy pushed outward across cosmic scales. By the time month over month Z14's ancient light reached Webb's detectors, the galaxy itself had been carried to somewhere between 32 and 35 billion light years from Earth. The light travelled 13.5 billion years. The source moved 32 billion light years away. Those two numbers seem like they should contradict each other. They don't. That's just what expanding space does to distances over enough time. Think about what that means for reachability. If you launched a ship at exactly the speed of light the moment month over month Z14's light arrived, pointed it straight at where that galaxy is right now, you would never close the gap. The space between here and there is expanding faster than light speed. You would travel forever at maximum velocity, and the destination would still be pulling away from you, year after year, billion of years after billion of years. Month over month Z14 is not just far. It is categorically, permanently, mathematically unreachable. Not with better engines, not with more time, not under any physical scenario permitted by the universe. And yet there it is. We can see it. That is the part that makes astronomers quiet for a moment when they think about it too long. Before month over month Z14 claimed the record, another galaxy held the title. JADD-SGS Z140, discovered through the James Webb Space Telescope's Deep Survey program called JADES, sits at a redshift of 14.32. That number means the universe has expanded by a factor of roughly 15 since this galaxy's light was emitted. Its light, too, left the source about 290 million years after the Big Bang. Two different galaxies, two different corners of the early universe, both showing us something that shouldn't have been possible to form so quickly. Both sitting so far beyond our reach that the distance is almost meaningless as a number. What stunned researchers about JADESGS Z140 was not just the distance, it was the galaxy itself. It was brighter than it had any right to be, more massive than the models predicted anything could get in only 290 million years. Stars take time to form. Galaxies take time to assemble. The physics of gravitational collapse has speed limits of its own. And yet here was this object, already enormous, already luminous, sitting in the very early universe like it had been there far longer than the timeline allowed. Current theories of galaxy formation do not fully explain it. The record holder before it was already a puzzle. The new record holder made the puzzle stranger. Webb keeps doing this. Every few months, another announcement, another redshift record, another smear of infrared light that turns out to be a galaxy from the universe's first few 100 million years. Each discovery pushes the observational frontier further back. Each one is genuinely astonishing as a feat of engineering and scientific patience. This is a telescope sitting 1,000,000 miles from Earth, cooling itself to temperatures near absolute zero, catching individual photons that have been traveling since before our solar system existed. The technology required to do this would have seemed like fiction to astronomers in the mid-20th century. But here is the thing that every new record quietly carries with it. Every time Webb finds a more distant galaxy, it finds a more unreachable one. The record books and the list of permanently inaccessible places are the same list. There is no discovery Webb can make that pushes us closer to the things it finds. The farther back we see, the farther beyond our reach those objects sit in the present. Month over month, Z14 exists right now, approximately 33 billion light years away, burning stars, evolving, possibly hosting something we cannot imagine. And we have no way to reach it, no way to signal it, no way to receive any new information from it. The light we see is 13.5 billion years old. The universe it came from is gone. What replaced it is beyond every horizon that matters. Webb's greatest achievement may be this. It showed us the birth of the cosmos in extraordinary detail, and in doing so made absolutely clear just how completely out of reach that birth actually is. We are staring at the birth of the universe with instruments our grandparents could never have imagined, and the things we're seeing are so far gone that no version of us will ever touch them. Seeing something and being able to reach it are two different things. And in most of the universe, they have almost nothing to do with each other. Think about what the previous section established. Month over month Z14 sits at a current distance of somewhere around 32 to 35 billion light years. We can see it. The James Webb Space Telescope pulled its light out of the noise and built an image from photons that have been crossing space since the universe was less than 300 million years old. That is a genuine triumph of human engineering and patience. And yet, month over month, Z14 is so far beyond our reach that the word unreachable barely captures it. Any signal we sent toward it today, traveling at the speed of light, would spend trillions of years falling behind as space expands faster than the signal can move. We will never touch that galaxy. We will never exchange a second message with whatever might exist there. Seeing it and reaching it are not two versions of the same possibility. They are completely separate facts about completely separate things. This is the paradox that most people miss entirely when they think about the size of the universe. The natural assumption is that if you can see something, you could in principle get to it. You might need a faster ship, you might need more time. But the thing is out there, the light arrived, so the path exists. That logic works perfectly well on Earth. It works inside our solar system. It even works for nearby stars, but it breaks down completely at cosmological distances. And it breaks down not because of any technological shortcoming, but because of something the universe is doing right now at every point in space, continuously and without any prospect of stopping. The observable universe stretches roughly 46 billion light-years in every direction. That sphere contains something like 2 trillion galaxies. 2 trillion. The number is large enough to be meaningless without some effort to feel it. 2 trillion separate islands of stars, gas, dark matter, each containing hundreds of billions of suns in many cases, each representing a place as complex and as vast as the neighborhood of space we call home. We can see all of them, at least in principle. Our telescopes are limited by sensitivity and wavelength and time, but the light from those galaxies has, in many cases, already crossed the distance and arrived. It is here. The photons exist. The observation is possible. 94% of those galaxies are beyond the cosmic event horizon, not beyond the edge of our instruments, beyond the edge of physics. Space at those distances is expanding faster than light, which means any photon those galaxies emit right now begins its journey already losing ground. It moves at the only speed available to it, the maximum speed the universe permits, and that speed is not enough. The gap grows. The photon never arrives, not in a billion years, not in a trillion. The expansion doesn't slow down enough to let it through, and in fact the expansion is accelerating, which means the situation gets worse over time rather than better. What we are actually seeing when we look at those distant galaxies is old light, ancient light, light that left when those galaxies were much closer to us, when the universe was younger and the expansion hadn't yet pushed them so far that their emissions became permanently stranded. The light made it here because it started its journey under better conditions, but those conditions are gone. The galaxy that sent the light has spent billions of years receding, and it now sits in territory that is, in the most literal physical sense, severed from us. We see it the way you might see the glow of a lighthouse that has since been demolished. The light reached you. The lighthouse is gone. What makes this genuinely strange is that the boundary between reachable and unreachable is invisible. There is no wall, no edge you could observe, no color change in the sky marking where the accessible universe ends and the severed portion begins. You can point a telescope at a galaxy sitting just inside the event horizon and a galaxy sitting just outside it, and they look identical. Both sets of photons arrived. Both images are real. One galaxy is, in principle, something a civilization with sufficient technology and patience might one day reach. The other is gone in a way that no technology and no patience can address, because the problem isn't patience, it's geometry. And the fraction of what we can see that falls into the reachable category is staggeringly small. The reachable portion of the observable universe isn't 10% or 20% or even 5%. It is a thin shell of nearby space, a small bubble of gravitationally accessible territory, surrounded by an enormous volume of galaxies we can photograph but never visit, signal but never contact, observe in exquisite detail, but never influence in any way. The museum analogy works here because museums are also places where you can look but not touch. But even that undersells it. In a museum, the painting stays on the wall. The distance between you and it doesn't grow. These galaxies are paintings that are actively moving away from you, framed in a corridor that lengthens every second, and the door behind you is already locked. 94% of what we can observe is already gone from our reach. Not in the future, not theoretically, but right now, today, permanently. In 1998, astronomers made a discovery so strange that the two teams who made it spent months checking their instruments before they trusted the result. They were not looking for anything revolutionary. Both groups were simply trying to measure how fast the universe's expansion was slowing down. Everyone assumed it was slowing down. Gravity pulls matter together. A universe full of matter should be decelerating, the way a ball thrown upward decelerates before it falls back to Earth. The only question was how much. Instead, they found the opposite. The expansion was speeding up, not slowing, accelerating. The universe was flying apart faster than it had been 1 billion years ago, faster than it had been 2 billion years ago, faster with every passing era of cosmic time. Nobody had predicted this. Nobody had even seriously entertained it as a possibility. The two teams were working independently, each studying a specific kind of exploding star called a Type Ia supernova. These explosions are useful to astronomers because they always release roughly the same amount of energy. If you know how bright something actually is, and you measure how bright it looks from Earth, you can calculate exactly how far away it is. Type Ia supernovae are cosmic distance markers, reliable enough to serve as the most precise rulers astronomers have at those scales. What both teams found was that the most distant supernovae were dimmer than they should have been. Not dramatically dimmer, but measurably, consistently, stubbornly dimmer. And the only explanation that fit was that those supernovae were farther away than expansion models predicted. The universe had stretched more than expected since their light set out. Something was pushing space apart faster than gravity could rein it in. They called it dark energy. The name is honest about exactly how little we understand it. Dark, because it emits no light, reflects no light, and interacts with nothing we can directly detect. Energy, because whatever it is, it has real physical consequences on the largest scales in the universe. Dark energy currently makes up roughly 68% of the total energy content of the universe. Ordinary matter, everything you can see, touch, measure, or collide, accounts for only about 5%. Dark matter makes up the rest. The universe you experience every day is a thin crust on top of something vast and invisible. What makes dark energy genuinely different from anything else physics has encountered is where it lives. It is not concentrated in objects. It is not denser near galaxies or thinner in the voids between them. Dark energy appears to be a property of space itself, a kind of pressure or tension built uniformly into the fabric of the universe at every point. And this leads to something almost paradoxical. Ordinary energy dilutes as space expands. Fill a room with gas, double the size of the room, and the gas gets thinner. Dark energy does not behave this way. As space expands, the amount of dark energy per unit volume stays constant, which means the total amount of dark energy in the universe grows as the universe grows. More space means more dark energy. More dark energy drives faster expansion. Faster expansion creates more space, which creates more dark energy. The cycle feeds itself endlessly with no break and no ceiling. This is why the event horizon you encountered earlier is not a fixed wall. It is a shrinking one. As dark energy accelerates expansion, the rate at which distant space recedes from us increases over time. Galaxies that are borderline reachable today, sitting just inside the boundary where a light speed signal might eventually close the gap, are being pushed across that boundary as the expansion rate climbs. The territory available to us is not holding steady. It is contracting, measured in cosmic time, and dark energy is the reason. What you could have theoretically reached 1 billion years ago, you cannot reach today. What you could theoretically reach today, a civilization 1 billion years from now could not. Physicists have proposed several explanations for what dark energy actually is. The most straightforward is something called the cosmological constant, a term Einstein originally introduced into his equations and then famously removed when he thought the universe was static. It describes a fixed energy density inherent to empty space. When observations confirmed accelerating expansion, the cosmological constant came back. It fits the data well, but it raises an immediate and unresolved problem. Quantum field theory predicts that empty space should contain an enormous amount of vacuum energy from the constant appearance and disappearance of virtual particles. When physicists calculate this predicted vacuum energy and compare it to the observed dark energy density, the numbers disagree by a factor of somewhere around 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an observation in the history of science. Other proposals exist. Some physicists suggest dark energy is not constant but changes over time, a dynamic field called quintessence. Some suggest gravity itself behaves differently on the largest scales than Einstein's equations describe. Some proposals involve extra dimensions. None of them are proven. None of them cleanly resolve the mystery. What is certain is that something is out there, real and measurable, threading through every cubic meter of space in the universe, pushing everything apart faster with every billion years that pass. Dark energy is not a theory scientists are comfortable with. It is an observation they cannot explain, a force they cannot see, accelerating the universe's expansion toward a future that gets lonelier with every passing billion years. The light reaching your eye from a distant galaxy has been on a journey so long that the universe it left no longer exists. The galaxy that sent it may have merged with a neighbor. The stars that lit it may have burned out. The space it crossed has stretched by billions of light years in the time it spent traveling. And the light itself has changed. It is not the same light that left. Space did something to it along the way. Here is what expansion does to a photon. Imagine drawing a sine wave on a rubber band, a smooth, repeating wave, crest to trough, crest to trough. Now stretch the rubber band. The wave stretches with it. The crests are farther apart. The troughs are farther apart. The wavelength has grown. The frequency has dropped. Nothing about the wave was touched directly. You only stretched the surface it was drawn on, and the wave changed anyway. That is exactly what happens to light crossing an expanding universe. The photon travels through space, and space itself is the rubber band. As space stretches, the light's wavelength stretches with it. A photon that left a distant galaxy as blue light, short wavelength, high frequency, can arrive at your telescope as red light, or infrared, or, if the journey was long enough, as a radio wave. The light has been pulled apart by the expansion of the universe over billions of years. This is not the same thing as the Doppler effect, though people often confuse the two. The Doppler effect is what happens when a source of sound or light is physically moving toward you or away from you through space. A train horn drops in pitch as the train passes because the sound waves are being compressed on approach and stretched on departure. The galaxy is moving and the motion shifts the light. Cosmological redshift is different. The galaxy is not speeding away through space. Space itself is growing between you and the galaxy, and that growth stretches the photon in transit. It is a physical stretching of the wave, not a velocity effect. The distinction matters because the math behind each process is different, and the distances involved are completely different scales. The name for this stretching is redshift. When astronomers talk about a galaxy's redshift, they are describing how much its light has been stretched during the journey to us. The measurement is given as a number, the letter Z. A redshift of 0 means no stretching happened. The galaxy is effectively right next to us. A redshift of 1 means the wavelength of the light has doubled by the time it arrived. The universe expanded enough during the photon's travel to stretch the wave by a factor of 2. A redshift of 5 means the wavelength arrived 6 times longer than when it left. And a redshift of 14, the kind associated with the farthest galaxies the James Webb Space Telescope has pulled from the darkness, means the wavelength is 15 times longer than when it was emitted. The universe expanded by a factor of 15 while that light was crossing space. That is the scale of expansion recorded inside a single number. What makes redshift so powerful is that it does not just tell astronomers how far something is, it tells them when the light left. A high redshift means the photon spent a long time in an expanding universe, which means it left a very long time ago, which means the object emitting it existed at an early point in cosmic history. When you read a galaxy's redshift, you are reading a timestamp. You are looking at an object as it existed at a specific moment in the early universe, not as it exists now. The galaxy at redshift 14 existed roughly 280 million years after the Big Bang. That is younger than the oldest known stars in our own galaxy today. The light did not simply travel far, it traveled through time in the only direction time allows, and the stretching of its wavelength is the physical record of every billion years it spent crossing expanding space. Astronomers did not always know how to read this. The first observations of redshifted galaxies, taken by Vesto Slipher in the early 1900s, looked like a straightforward velocity measurement. Galaxies appeared to be moving away. Edwin Hubble later connected the redshift to distance, and the pattern that emerged revealed something enormous. The farther a galaxy was, the more its light was redshifted, which meant the more space had expanded during the photon's journey. The redshift was not describing speed, it was describing cosmic expansion accumulated over the entire path of the light. Today, redshift is the primary tool for mapping the structure of the observable universe. Spectroscopes on telescopes like Webb split incoming light into its component wavelengths and measure exactly where known spectral lines have shifted from their expected positions. Each element emits light at characteristic wavelengths, fingerprints written in physics. When those fingerprints are found at longer wavelengths than expected, the shift is measured and converted into a redshift value. From that value, astronomers calculate the expansion factor, the light travel time, and the moving distance to the object. A single number, derived from the color of ancient light, unlocks the history of the photon's entire journey. The further the redshift, the more the universe has grown since that light began its journey. And reading that number is how astronomers reach back through time without moving an inch. Every year, roughly 160 billion stars cross the cosmic event horizon and leave our reach forever. Not in an explosion, not in a collapse. Nothing marks the moment. From our end, there is no signal, no flicker, no final goodbye. The stars just keep burning on the other side of a line we drew with mathematics, and from that point forward, any light they produce will travel toward us for the rest of time without ever arriving. The expansion of space at their location has tipped past the speed of light, and that means the gap between us and them grows faster than light can close it. They are gone the way a ship disappears over the horizon. Not destroyed, just permanently out of reach. What makes this strange is that we don't lose them all at once. The crossing is continuous. Right now, as you read this, stars are sliding over that boundary in an unbroken stream. 160 billion per year works out to roughly 5,000 stars every single second, each one a sun, many of them larger than ours. Some of them almost certainly orbited by planets. Some of those planets may have liquid water on their surfaces, and all of that is now permanently beyond the boundary of anything we can ever touch, signal, or influence in any way. Think about what 160 billion actually means. There are an estimated 100 to 400 billion stars in the Milky Way. So in a single year, we lose something approaching the entire stellar population of our galaxy, not in reality, but in terms of reachability. Every year, a galaxy's worth of stars slips past the threshold. By the time a child born today turns 30, the universe will have shed the equivalent of roughly 30 Milky Ways from our accessible territory. The loss is enormous. It is quiet, and it never stops. What's left inside our event horizon is a fraction of what we can see. The observable universe stretches 46 billion light years in every direction. That boundary is defined by old light, by photons that set out billions of years ago when those distant regions were much closer to us than they are today. Observability and reachability are two completely different things. When you account for how far we can actually send something, even at light speed, even with infinite time, the picture collapses. About 97% of the observable universe by volume is already beyond our reach. Not eventually, not theoretically. Right now, today, a light-speed ship launched toward the vast majority of what our telescopes can see would never arrive. The destination would recede faster than the ship could close the distance. The ship would travel forever and cover the gap never. The 3% sitting inside our reachable territory still sounds like a lot until you map it against the full sphere of what we can observe. Picture the entire observable universe as an ocean. Every galaxy, every star, every wisp of intergalactic gas you could see from the most powerful telescope ever built, that's the whole ocean. The territory we could theoretically reach, even with light speed and endless patience, is roughly a tide pool at the edge of one shore. Everything else is open water with no bottom and no far bank. There is something worth sitting with here. The universe we observe is mostly a museum. We can look at the exhibits, we can study them, we can measure the light they emit with extraordinary precision, but we are locked out of the building. The glass between us and them is not technology we haven't invented yet. It is not a funding problem. It is the expansion of space itself, operating at speeds that no propulsion system can compete with, because no propulsion system is operating on the same playing field. We are moving through space. Space is moving, and at most of these distances, space is winning. What gets lost in the statistics is the texture of what's out there. Beyond the event horizon aren't just abstract coordinates. There are galaxy clusters older than our solar system. There are stars in the final stages of collapse. There are almost certainly planets with geologies and atmospheres, and maybe something looking up at its own night sky right now, wondering what's beyond what it can see. All of that exists. We know it exists because we can see the light it sent us when it was younger and closer. But the version of those places that exists right now is locked away. Whatever those stars are doing tonight is information that will never reach us. Their present is invisible to us permanently by physics, by the mathematics of expansion with no loophole. The event horizon is not a wall with a door. It is not a boundary that future generations will eventually push past with better engines or better ideas. It is a calculation that worsens over time because dark energy keeps accelerating the expansion, which means each year the threshold falls slightly closer to us, and each year the number of stars crossing it per second ticks upward. The universe accessible to us is not stable. It is contracting slowly in terms of what we can ever hope to interact with, even as the observable sphere around us, defined by old arriving light, holds roughly constant. The universe isn't hiding those stars from us. They're still out there, still burning, still emitting light. We just live in a cosmos where the space between us is growing faster than any message they send can travel. There is a specific distance from Earth beyond which any signal sent right now at the speed of light will never arrive. Not delayed, not weakened, never arriving. The photon leaves its source at the maximum speed anything in the universe can travel, and it still loses. Space expands faster than the photon can move through it, and the gap between that photon and Earth grows wider every second of every year until the end of time. That boundary sits at roughly 16 to 18 billion light years away. Everything beyond it is cut off from us, not by distance alone, but by physics that has no workaround. This is the cosmic event horizon, and it is not the same thing as the edge of the observable universe. Those two numbers get confused constantly, and the confusion matters. The observable universe stretches about 46 billion light years in every direction. That number represents light that has already arrived, photons that made the journey successfully because they were emitted billions of years ago when the universe was smaller and expansion was slower. The 18 billion light-year wall is different. It is not about the past. It is about right now, this moment, and every moment going forward. Any source of light sitting beyond that threshold today is sending photons toward us that will never make it. The journey begins. The photon races outward at full speed, and space simply grows faster than it can run. To understand why the wall sits where it does, you have to think about what determines it. The event horizon is not a fixed number carved into the structure of reality. It is a calculation, and it changes as the expansion rate changes. Right now, space at a distance of roughly 16 to 18 billion light years is expanding fast enough that light cannot bridge the gap from there to here. If the expansion rate was slower, that boundary would sit farther out. If dark energy pushes expansion faster over time, the boundary moves closer to us. The wall is not a permanent address, it shifts. And the direction it tends to shift, given that dark energy appears to be accelerating expansion, is inward. The universe we can receive signals from is not the same size it was 1 billion years ago. It is smaller, and it will be smaller still 1 billion years from now. Here is what makes this genuinely strange. Objects beyond 18 billion light years are not invisible to us. We can still see ancient light from galaxies far beyond that threshold, because that light was emitted long ago when those galaxies were closer and expansion was slower. The photons completed their journey because they started when conditions allowed it. But those same galaxies, if they are emitting light right now, are producing photons that will never reach us. We are watching the final transmissions from a region of space that has already gone permanently silent in every forward-looking sense. The galaxy is still there. It is still burning. We just will not receive another message from it, ever. Think about what that means for the physics involved. A photon leaves a galaxy sitting 20 billion light years away. It is moving at the speed of light, the fastest anything can travel through space. In its first 1,000,000 years of travel, it covers enormous ground. But space at that distance is expanding fast enough that the photon's position relative to Earth barely improves. Then, as the photon travels into regions of space that are expanding even faster, the ground it has already covered starts working against it. The photon does not slow down. It is still moving at full speed through its local patch of space. The problem is that the patch itself is moving away from us faster than the photon can advance. The gap does not close, it grows. The photon travels for 1,000,000,000,000 years and is no closer to us than when it started. Eventually, the expansion of space carries it further from Earth than it was at the moment of emission. The wall is not dramatic when you are near it. There is no sign, no physical barrier, nothing to observe. A civilization living in a galaxy 20 billion light years from Earth today would not experience anything unusual. Their physics work the same as ours. Their photons travel at the same speed. From their perspective, they exist in the center of their own observable universe, surrounded by light from a sphere of space they can see, but mostly cannot reach. They may have detected our galaxy in ancient light from billions of years ago. They may have astronomers who study it. They almost certainly cannot know that any signal they send toward us right now will fail. The expansion rate at the boundary between us and them exceeds the speed of light, quietly and without announcement, and neither civilization has any way to detect the moment the door closed. The number 18 billion light years does not sound that different from 13.8 billion, the age of the universe, or from 46 billion, the observable radius. It is easy to let the numbers blur together, but the distinction carries real weight. Everything inside that wall can still communicate with us in principle. Everything outside it already cannot. And the wall is not holding steady. Somewhere out there, 20 billion light years away, a civilization might be sending us messages right now that will travel for trillions of years without ever closing the gap. There are two different kinds of horizons in cosmology, and most people, including a lot of science communicators, treat them as the same thing. They are not the same thing. They are not even close to the same thing. They sit at different distances. They arise from different physics, and they carve the universe into completely different sets of places. Conflating them is one of the most common ways that explanations of cosmic scale go wrong. And once you see the distinction clearly, you start to realize how much stranger the situation actually is than anyone usually lets on. Here is the first horizon. Astronomers call it the particle horizon, and it marks the edge of the observable universe. Everything inside this boundary has had enough time to send light that has already reached us. The light that defines this edge set out roughly 13.8 billion years ago from matter that was, at that moment, extraordinarily close to us in a young and dense universe. Space has expanded so much since then that the objects which emitted that ancient light are now sitting roughly 46 billion light years away. That is the particle horizon. That is how far you can see. It is entirely a statement about the past. Light already travelled, signal already sent, message already received. Here is the second horizon. The event horizon marks the edge of reachability. It is the boundary beyond which anything you send right now, at any speed up to the speed of light, will never arrive. This boundary sits at roughly 16 billion light years away, not 46 billion, 16. That is not a rounding error. That is a fundamentally different number arising from a fundamentally different question. The particle horizon asks how far back in time you can see. The event horizon asks how far forward in space you can ever go. Two questions, two answers, separated by 30 billion light years of universe that you can observe but never touch. Picture a map. Draw a circle representing everything you can see. That circle has a radius of 46 billion light years and contains hundreds of billions of galaxies visible in principle to a powerful enough telescope. Now draw a second circle on the same map, centered on the same point. This one represents everything you can ever reach. Its radius is a fraction of the first. The second circle sits inside the first the way a marble sits inside a stadium. Most of the stadium is simply out of bounds, not because you lack the right shoes, because the floor of the stadium is stretching away from you faster than you can walk toward the far wall, and it has been doing so for billions of years, and it is not going to stop. What makes this deeply strange is that the things you can see but cannot reach are not illusions. They are real galaxies, burning real stars, governed by real physics, potentially hosting real planets. The light arriving from them is genuine. You are genuinely observing them. But the version of those galaxies sending you that light is a version from billions of years in the past, from a time when they were vastly closer. That ancient light beat the expansion. It started its journey when the universe was smaller, when the distance was manageable, and it has spent all this time crossing the gap. But a photon sent from those same galaxies today? That photon loses. It will travel in our direction for trillions of years, and the space between will grow faster than the photon closes the gap. The signal never arrives. The message is never received. This is the distinction that matters. Observability looks backward. It is a record of what light has already accomplished. Reachability looks forward. It is a limit on what any future signal can ever accomplish. You cannot trade one for the other. The fact that you can see a galaxy 40 billion light years away tells you absolutely nothing about whether you can reach it. In almost every case, you cannot. Not eventually, not with patience, not with better engines. The geometry of expansion simply does not allow it. Were there civilizations in those distant galaxies when that light left? There is no way to know. Are they still there? No way to know that either. Whatever they were doing 12 billion years ago, when that light began its journey, they have had 12 billion more years of history that we will never observe, because the light from those subsequent 12 billion years will never reach us. The version of those galaxies we see is the only version we will ever get. Frozen, ancient, beautiful, and completely, permanently out of reach. This is why astronomers draw a careful line between what the James Webb Space Telescope can observe and what humanity could ever, in any realistic or even theoretical sense, visit. Webb is peering into the particle horizon. It is reading ancient messages. It is not identifying destinations. Every record-breaking detection at the edge of the observable universe is simultaneously a record-breaking demonstration of unreachability. The farther back Webb sees, the more certainly those objects are stranded on the wrong side of the event horizon. The universe you can see and the universe you can touch are almost entirely different universes, and the overlap between them is heartbreakingly small. Not everything in the universe is being pulled away from us. That fact might come as a relief after everything that precedes it. The event horizon, the 94%, the galaxies slipping beyond reach every year, all of that is real, and none of it is going away. But gravity still wins in certain places, and the places where it wins are the places we actually live. Understanding where the expansion stops is not just a technical footnote, it is the boundary of our permanent home. The local group is the name astronomers give to the cluster of galaxies bound together by their mutual gravity. It contains roughly 80 galaxies. Most of them are small, dwarf galaxies, satellites, irregular scraps of stars that orbit larger neighbors. But the group has two dominant members. The Milky Way, our own galaxy, roughly 100,000 light-years across, containing somewhere between 100 and 400 billion stars. And Andromeda, the largest galaxy in the neighborhood, a spiral about 2.5 million light-years away that you can actually see with your naked eye on a dark night as a faint smear of light in the constellation of the same name. The Magellanic Clouds, two irregular satellite galaxies orbiting the Milky Way, are also in the group. So are Triangulum, a smaller spiral, and dozens of faint dwarf galaxies scattered around the edges. The critical thing about all of them is this: they are not receding. The space between them is not expanding. Cosmic expansion operates across the large-scale structure of the universe, across the vast voids between superclusters of galaxies, across distances so enormous that the density of matter is effectively zero and gravity has nothing to grip. But inside gravitationally bound systems, the fabric of space does not stretch. Gravity holds it still. The local group is one of those bound systems, locked together by the combined mass of everything inside it, and the expansion happening everywhere else simply does not apply within its borders. This is not intuitive. If space is expanding everywhere, why doesn't it expand inside our galaxy? The answer is that expansion is not a force pushing things apart. It is a tendency in regions where nothing else is acting. Where gravity is strong enough, it overcomes that tendency completely. The Milky Way itself is not getting larger. The solar system is not getting larger. The distance from Earth to the Moon is not being nudged outward by the expansion of space. On these scales, gravity dominates so thoroughly that expansion is irrelevant. It only becomes relevant when you zoom out past the scale where gravity can hold things together, past galaxy clusters, out into the true void. What this means for the Milky Way and Andromeda is something most people find startling the first time they hear it. These two galaxies are not moving apart. They are falling toward each other. Andromeda is approaching the Milky Way at roughly 110 kilometers per second. In about 4.5 billion years, they will collide. Not crash violently the way two cars crash, Stars are far too spread out for individual stars to actually strike each other, but the two galaxies will pass through one another, their gravitational fields tangling, their spiral structures shredding, their stars scattering into new orbits. Over the course of 1 billion years or so after the initial pass, they will merge into a single large elliptical galaxy. Astronomers have already modelled what this will look like. The name they use informally is Milkomeda. Whatever the Sun looks like at that point, if it still exists, it will be orbiting inside a combined galaxy that looks nothing like either of its parents. This merger is not an exception to the rule. It is the rule. Bound systems stay bound. They evolve, they interact, they merge, but they do not drift apart on the expansion current. Over cosmic timescales, the entire local group will likely settle into a single large mass, the remnant of all those gravitational interactions accumulated over billions of years. Beyond the local group, the picture shifts. Nearby structures like the Virgo cluster and the broader local sheet share some gravitational connection with the local group, but even these affiliations weaken with distance. The Virgo cluster, roughly 65 million light-years away, is the center of the larger supercluster we sit in, called Laniakea. But the expansion of space is already doing significant work at those distances. What lies beyond that is simply receding. The thousands of galaxy clusters visible across the observable universe, each containing hundreds or thousands of galaxies, are all moving away. Their internal gravity holds them together, but the space between them and us grows without limit. Here is the thing worth sitting with. The local group is not a temporary campsite. It is permanent territory. It is all the territory we will ever have. Every galaxy we can see beyond it, all those hundreds of billions of distant points of light, will eventually recede beyond any possible reach. The universe, as experienced from our corner of it, will narrow, not in any time frame that matters to humans, but across the deep future. The accessible universe will shrink down to this one-bound collection of galaxies and nothing more. Everything beyond that bound cluster of galaxies is drifting away on a current we cannot swim against, and over enough time, the local group will be the only territory we ever had. Humanity has been broadcasting into space for about 100 years. The first radio signals strong enough to escape the atmosphere went out in the early 20th century, and those signals have been traveling at the speed of light ever since. That sounds impressive until you do the math. 100 years of travel at light speed puts our earliest broadcasts roughly 100 light-years from Earth. In a galaxy that is 100,000 light-years across, that is nothing. A bubble 100 light-years in radius containing our entire history of radio transmission would fit inside the Milky Way more than 1 billion times over. We have not even whispered across the room. Think about what that sphere actually contains. 100 light-years out, our signals are washing over a few hundred stellar systems at most. Most of those systems have no planets capable of receiving anything. The signal itself has weakened enormously over that distance, spreading out across an expanding shell of space, thinning with every passing light year. By the time any of our early broadcasts reach even the nearest stars beyond the immediate solar neighborhood, they are not a signal anymore. They are noise. The energy has diluted so completely that distinguishing it from background radiation would require instruments far beyond anything we currently understand. We sent our voice into the dark, and the dark swallowed it almost immediately. Physical objects have fared no better. Voyager 1, launched in 1977, is the most distant human-made object ever built. After more than 40 years of continuous travel, it has crossed the boundary of the heliosphere and entered interstellar space. That achievement is genuinely extraordinary. Voyager is now roughly 23 billion kilometers from the Sun. In light travel time, that is about 22 hours. The nearest star system, Alpha Centauri, sits about 4.2 light-years away. At Voyager's current speed, it would take approximately 75,000 years to cover that distance. Not 75,000 years to reach the edge of the galaxy. 75,000 years to reach the next star over. The Milky Way's nearest large neighbor, Andromeda, is 2.5 million light-years away. Voyager would need something like 30 billion years to get there, which is roughly twice the current age of the universe. These numbers collapse any instinct that we are a spacefaring civilization in any cosmologically meaningful sense. We have sent 2 small probes into interstellar space, and they are traveling at speeds so slow that they are essentially parked by the standards of the galaxy. Our fastest spacecraft ever launched moved at roughly 70 kilometers per second. Light moves at 300,000 kilometers per second. The ratio is about 1 to 4,000. If the speed of light were a highway at 100 miles per hour, our fastest probe is doing roughly 100th of a mile per hour. We are not crossing the street at that pace. We are barely shifting our weight. Now flip the picture entirely. Somewhere out there may be a civilization that sent signals of its own billions of years ago. Those signals may be passing through our part of the galaxy right now, but they originated in a galaxy that has since aged by billions of years. The stars that powered that civilization may have already burned out. The planets may be cinders or may have been swallowed by expanding red giants. The civilization itself may have risen and collapsed 100 times over in the interval between when it sent that signal and when the signal reaches us. We could theoretically receive a message from something that no longer exists in any form we would recognize. The signal survived. The sender did not have to. That asymmetry runs in both directions. Our own broadcasts are a record of a civilization that existed between roughly 1920 and now. If any of those signals were received by someone 80 light-years away right now, they would be hearing transmissions from the early days of radio. No digital signals, no satellite television, no internet. Whatever image they piece together of us is built from something we have already discarded entirely. The signal is not just weak, it is old. By the time it arrives anywhere meaningful, it will be a fossil. What we have actually sent, in any cosmological sense, is almost nothing. Our radiosphere is smaller than most of the molecular clouds drifting through our own galaxy. Our fastest probes will never reach another star system in any time frame relevant to human civilization. Our most powerful transmissions, the deliberate high-powered radio messages we have aimed at specific targets, will arrive at their destinations decades or centuries from now, so weakened by distance that detection would require almost miraculous sensitivity on the receiving end. We imagine ourselves broadcasting loudly into the cosmos. The reality is closer to someone whispering into a hurricane from the bottom of a canyon. The local group holds roughly 80 galaxies. Our signals will not meaningfully reach even our nearest galactic neighbors in any timescale relevant to our existence as a species. The Milky Way itself will take our radio bubble tens of thousands of years to cross. Beyond the Milky Way, there is nothing coming from us that the universe will notice or remember. We exist, in signal terms, as a barely detectable fluctuation in one corner of one galaxy among hundreds of billions. Our fastest message is a ripple in a pond the size of a continent, and the shore we're trying to reach is not on the same planet. Imagine being born into the universe as it will exist 1,000,000,000,000 years from now. Not 1 billion, not 10 billion, 1,000,000,000,000. The number is large enough that it loses meaning almost immediately, so consider what it actually implies. 1,000,000,000,000 years from now, the universe will be roughly 70 times older than it is today. Every process happening in the cosmos right now, star formation, galaxy collisions, the slow churn of gas clouds into new suns, will have either concluded or slowed to nearly nothing. The sky will not look the way it looks tonight. In about 100 billion years, every galaxy beyond the local group will have crossed the event horizon. Not dramatically, not all at once. They'll go one by one, silently, their light stretching to wavelengths too long to detect, their signals fading below any threshold a physical instrument could measure. By the time 1,000,000,000,000 years have passed, that process will be ancient history. The observers of that future era won't watch it happen. They'll simply inherit a sky where it already happened long ago, the way we inherited a sky where the Big Bang already happened long ago. They'll have no memory of a fuller universe, because no memory could survive that long. What would those observers actually see? The merged remnant of the Milky Way and Andromeda, a single enormous elliptical galaxy sometimes called Milkomeda by astronomers who like to think that far ahead. Around it, the smaller satellites of the local group, still gravitationally bound, still held close. Beyond that, nothing. Not dim, not faint, not sparse. Nothing. The intergalactic void will be dark in every wavelength that matters. No smudges of distant galaxies, no faint arcs of gravitational lensing from massive structures far away. The universe, from where those observers stand, will appear to be a single island of stars floating in an infinite and otherwise empty sea. Here is the part that should stop you cold. Those future observers will be wrong about the universe in almost every fundamental way, and they will have no way to know it. Right now, we can measure the cosmic microwave background, the afterglow of the Big Bang, stretched into microwave frequencies, filling the entire sky from every direction with the same faint glow. It is the single most powerful piece of evidence we have that the universe began in a hot, dense state and has been expanding ever since. 1,000,000,000,000 years from now, that signal will be gone, stretched beyond any possible detection. The future observers will have no cosmic microwave background. They'll have no evidence of the Big Bang, not because it didn't happen, but because the evidence will have redshifted into oblivion. They'll look at their galaxy and see stars. They'll do their physics. They'll be intelligent, careful, rigorous, and they'll build models of the universe based on what they can observe. Those models will tell them they live in a static, isolated system. Perhaps they'll believe the universe is eternal and always looked this way. Perhaps they'll believe their galaxy is the entirety of existence. The data available to them will support those conclusions. The data that would contradict those conclusions will be permanently beyond the horizon, already gone. They will not be making mistakes. They will be doing exactly what we do, looking at the available evidence and drawing the best conclusions the evidence supports. Their evidence will simply be catastrophically incomplete. This is what makes the situation genuinely unsettling, not just philosophically, but scientifically. We think of scientific knowledge as something that accumulates, that builds, that grows more complete over time. But the universe does not guarantee that. The observable universe is not growing. It is shrinking. The information available to any civilization exists inside a window, and that window closes over time as expansion carries more and more of the universe beyond the event horizon. We happen to live during a window that is still remarkably open. We can see the cosmic microwave background. We can see distant galaxies receding at speeds we can measure. We can detect the large-scale structure of the universe, the vast filaments and voids that formed from the earliest density fluctuations after the Big Bang. All of that evidence is visible to us right now, today. 1 trillion years from now, none of it will be. The large-scale structure, the distant galaxies, the microwave background, all of it will have crossed the horizon. Every measurement that tells us the universe is 13.8 billion years old will be inaccessible. Every redshift that tells us expansion is accelerating will be undetectable. The future observers will be sharp, capable, perhaps more technologically advanced than we are by almost any measure. It won't matter. The universe will have simply moved the evidence beyond their reach before they arrived. They'll look out at an empty sky and conclude they understand the cosmos, and their conclusion will be almost entirely wrong. Every piece of evidence that would allow them to understand what the universe really is would have drifted beyond the horizon before they ever developed the instruments to look for it. The galaxies are not going to vanish in any dramatic sense. There will be no explosion, no collision, no moment where the sky suddenly goes dark and someone notices. What happens instead is slower, quieter, and in some ways far stranger than any catastrophe. The light from distant galaxies will simply stretch, it will redden, it will dim, and over timescales so long that human history is less than a blink inside them, it will fall below the threshold of anything we could ever detect. The universe isn't ending, it's fading. To understand how this works, you have to remember what happens to light as it travels through expanding space. Space doesn't just carry light from one place to another, it stretches the light as it goes. Every photon traveling toward you from a distant galaxy is being pulled at both ends by the expansion happening underneath it, the way a wave drawn on a rubber band gets longer when you stretch the band. The wavelength increases, and wavelength determines everything about what kind of light you're looking at. Short wavelengths are blue, longer wavelengths are red. Longer still, and you're in infrared, invisible to the naked eye but detectable with the right instruments. Longer than that, and you're in radio waves. Longer than that, and you're in wavelengths so enormous that no telescope we could physically build would ever register them. That is where the light from the most distant galaxies is headed. Not into darkness in any sudden sense, but into a frequency so low that it becomes indistinguishable from nothing. A galaxy sitting near the edge of our observable universe right now is all redshift so redshifted that its light arrives as stretched, dim infrared. Give it tens of billions of years more of expansion, and that same light, or rather the new light that galaxy keeps emitting, will shift further still. First into the far infrared, then into microwave wavelengths, then into radio, then into wavelengths longer than anything our instruments could conceivably capture. The galaxy doesn't blink out, it whispers its way into silence. The timescales here are almost offensive to intuition. In about 100 billion years, the most distant galaxies currently visible will have faded to the point where even the most sensitive instruments imaginable would struggle to find them. 100 billion years. Our sun has been burning for less than 5 billion. The entire history of complex life on Earth fits inside a few 100 million. 100 billion years is so far beyond any human frame of reference that the number might as well be infinite. And yet, in cosmic terms, this is simply what expansion does when you let it run long enough. What makes this stranger still is that the cosmic microwave background is already halfway through this process. The CMB is the afterglow of the early universe. About 380,000 years after the Big Bang, the universe cooled enough for hydrogen atoms to form, and the flood of light that had been trapped in the hot plasma was suddenly released. That light has been traveling ever since, and the whole time it's been traveling, space has been stretching it. What started as high-energy radiation, hot enough to ionize matter, has already been stretched down into microwave wavelengths by the time it reaches us. We detect it today as a faint, uniform hiss of radiation arriving from every direction in the sky. It is already a ghost of what it was, and it will keep stretching. In the far future, the CMB will shift from microwaves into radio waves, then into wavelengths too long for any detector. The universe's oldest light will quietly stop being detectable. Not because it's gone, because it's too stretched to see. There is something almost meditative about this picture if you sit with it long enough. No stars are being extinguished ahead of schedule. No galaxies are being destroyed. Everything is simply moving apart, and the light everything emits is being pulled thinner and thinner across an ever-growing distance. The energy is still there. The photons are still there. They've just been spread so thin across such enormous wavelengths that they carry almost no detectable information by the time they arrive. Or they don't arrive at all, because the expansion outran them before they could close the gap. What you are looking at when you consider the long-term fate of the observable universe is the most gradual dimming in the history of physics. No event triggers it. No mechanism turns it off. It is simply what happens when space keeps expanding and light keeps stretching and time keeps passing. The sky will grow emptier over hundreds of billions of years. The radio whispers of distant galaxies will get quieter. The cosmic microwave background will fade below any threshold. And eventually the universe, as seen from any vantage point within it, will consist of the local gravitationally bound structures and an expanse of darkness beyond them that contains nothing detectable at any wavelength. The light is still out there. We just can't reach it anymore, in any sense of the word reach. It is the universe slowly going quiet, the way a fire goes out, not when someone throws water on it, but when the last of the wood burns down to ash. There is no tape measure long enough, no laser precise enough, no experiment direct enough to simply measure the distance to a galaxy billions of light years away. And yet astronomers have numbers, precise ones, numbers that tell us a galaxy is 32 billion light years away, not 30, not 35. How do you get those numbers with no ruler? The answer is a structure so carefully built that it spans from our own backyard to the edge of the observable universe, each layer stacked on the one below. Astronomers call it the cosmic distance ladder. And like any ladder, if the bottom rung breaks, everything above it falls. The first rung is the only one that requires almost no assumptions at all. It's called parallax. Hold your finger in front of your face and close one eye, then the other. Your finger appears to shift against the background. Your two eyes are separated by a few inches, and that tiny gap is enough to create an apparent shift that your brain converts into depth. Astronomers do the same thing with Earth's orbit. In January, you observe a nearby star and record its exact position against the background of far more distant stars. In July, Earth has moved to the opposite side of the Sun, 186 million miles away. Observe the same nearby star again. It has shifted slightly. The size of that shift tells you the distance with basic trigonometry. No assumptions about the star's brightness or composition, just geometry. This works cleanly for stars within a few thousand light years. Beyond that, the shift becomes too small to measure accurately. Even with the best instruments we have ever built, the first rung only reaches so far. The second rung reaches much farther. It relies on a discovery made not by a famous male physicist at a major institution, but by a woman working as a human computer at the Harvard College Observatory in the early 1900s. Henrietta Leavitt was given the painstaking task of cataloguing the brightness of stars in photographic plates. While doing this, she noticed something extraordinary inside the Magellanic Clouds. Small satellite galaxies visible from the southern hemisphere. A class of stars called Cepheid variables pulse. They brighten, dim, and brighten again on a regular cycle. Leavitt discovered that the period of that pulse, the time it takes to complete one cycle, is directly related to the star's true luminosity. A slower pulse means a more intrinsically bright star, every time, without exception. This is a gift of almost absurd usefulness. If you can measure how long a Cepheid takes to pulse, you know exactly how bright it actually is. Then you compare that to how bright it appears from Earth. The dimmer it looks compared to how bright you know it is, the farther away it must be. It is the same logic as watching a car's headlights on a highway. A very dim pair of headlights that you know belong to a powerful beam must be far away. Cepheids gave astronomers a way to reach into nearby galaxies and measure distances that parallax could never touch. Edwin Hubble used Cepheids in the Andromeda Galaxy in the 1920s to prove it was a galaxy at all and not just a cloud of gas within our own Milky Way. Without Leavitt's discovery, Hubble makes no discovery. Without Hubble's discovery, modern cosmology doesn't exist in any recognizable form. But even Cepheids have a limit. Past a certain distance, individual stars become impossible to resolve. The galaxy looks like a smear of light. You cannot find a pulsing star inside it because you cannot see individual stars at all. Here, the ladder needs a new rung, and it found one in exploding stars. A type Ia supernova happens when a white dwarf, the dense remnant of a dead sun-like star, pulls matter from a companion until it hits a precise critical mass and detonates. Because the trigger point is always the same mass, the explosion is always roughly the same brightness. Always. These supernovae are bright enough to outshine entire galaxies for a few weeks. That brightness can be detected across billions of light years. Measure how bright it appears. Compare it to how bright you know it must be, and you have a distance. This is the rung that reaches farthest. This is also the rung that, in 1998, told two independent research teams that the universe's expansion wasn't slowing down as everyone expected. It was accelerating. That finding won a Nobel Prize and introduced the world to dark energy. Then, for the most distant objects of all, the ladder hands off to redshift. The further a galaxy, the more its light has been stretched during the journey to us. Measuring the degree of that stretching gives you the redshift value, and from the redshift, combined with models of cosmic expansion, you get the distance. This last rung leans heavily on everything below it. It needs the expansion rate to be calibrated, which needs the supernova distances, which need the Cepheid distances, which need the parallax distances anchoring the whole structure at the bottom. Every rung depends on the one beneath it. An error introduced at the Cepheid level quietly corrupts every measurement above. This is not a theoretical concern. It is the reason cosmologists are currently arguing about the Hubble constant. Two measurement methods using different rungs produce different answers, and neither side has budged. The distance ladder is one of the most elegant constructions in science. Built rung by rung from our own solar system outward, each step relying on the one before it, until the measurements stretch back to the edge of the observable universe. There is a number at the center of modern cosmology, and right now, two different ways of measuring it are giving two different answers. That number is the Hubble constant. It describes how fast the universe is expanding. Specifically, how many kilometers per second a galaxy accelerates away from us for every megaparsec of distance between us. 1 megaparsec is about 3.26 million light years. The Hubble constant is the single most important number in cosmology. It determines the age of the universe, the size of the observable universe, and the rate at which the event horizon is closing in around us. Every figure discussed in this series sits downstream of it, and right now, physicists cannot agree on what it is. Here is the problem in plain terms. There are two main ways to measure the Hubble constant, and they disagree, not by a little, not by a rounding error. They disagree by roughly 10%, and that gap has refused to close for years. The first method looks backward. Scientists use the cosmic microwave background, the faint ancient glow of radiation left over from about 380,000 years after the Big Bang, to reconstruct the early universe with extraordinary precision. From that reconstruction, they can calculate how fast space should be expanding today based on the standard model of cosmology. That calculation gives a Hubble constant of about 67 kilometers per second per megaparsec. The Planck satellite, which mapped the microwave background in extraordinary detail, consistently returns numbers in that range. The second method looks at the nearby universe directly. It uses the distance ladder described in the previous section: Cepheid variable stars, Type 1a supernovae, standard candles stacked on top of standard candles, to measure distances to galaxies independently and calculate the expansion rate from observation rather than calculation. That method gives a Hubble constant of roughly 73 kilometers per second per megaparsec. The SH0ES collaboration, which has refined this measurement for years using Hubble Space Telescope data and more recently James Webb data, keeps landing in the same place. 67 versus 73. The universe either expanded more slowly than the early evidence suggests, or it has been expanding faster than the theory predicts. Both cannot be right at the same time. This is what physicists call the Hubble tension, and it has become one of the most heated arguments in modern physics. For a while, many researchers assumed the tension would dissolve. Measurements would sharpen, calibrations would improve, and the two numbers would converge. That is not what happened. As instruments became more precise, the discrepancy held. In some analyses, it grew slightly. Each refinement that should have resolved the disagreement instead confirmed it. The tension is real. There are two broad categories of explanation. The first is that someone is making a systematic error. Maybe the distance ladder has a flaw buried deep in one of its rungs. Maybe the Cepheid calibrations are off because of dust absorption that wasn't properly accounted for. Maybe the supernova brightness assumptions contain a subtle bias. Researchers have looked hard at every one of these possibilities. So far, none of them has produced a clean confession. Webb data was supposed to settle this. It didn't. The higher number stayed high. The second category is more disquieting. Maybe nobody is making an error. Maybe the standard model of cosmology, the framework that has held together for decades and predicted the observable universe with stunning accuracy, is incomplete. If the tension is real and not a measurement problem, it implies the universe did something that the current model does not account for. Some physicists have proposed that the early universe went through a brief phase of accelerated expansion beyond what standard inflation describes, something called early dark energy that would have changed the acoustic scale of the microwave background and pushed the inferred expansion rate up. Others have suggested that dark energy is not constant over time, that it may have varied in strength as the universe aged, which would shift the numbers in ways that current models cannot accommodate. A few researchers have explored modifications to gravity itself. None of these proposals has gathered enough evidence to replace the standard picture. They are live possibilities, not answers. What makes the Hubble tension genuinely unsettling is that it sits at the foundation. This is not a disagreement about some obscure corner of astrophysics. It is a disagreement about the central number that everything else is built on. The age of the universe shifts depending on which value you use. The size of the observable universe shifts. The timeline of structure formation shifts. The event horizon calculation shifts. If the tension resolves in favor of the higher number, every figure in cosmology that depends on the expansion rate will need to be revisited. Either someone is making an error that nobody has found yet, or the standard model of cosmology is missing something that, once found, will change everything built on top of it. The expansion of space does not rip galaxies apart. This surprises a lot of people when they first hear it, because the story up to this point has made expansion sound like a force that touches everything, that stretches all distances, that makes every point in the universe move away from every other point. And that is true as far as it goes. But there is another force operating in the universe, one that has been here far longer than any cosmologist, and it has opinions about what expansion gets to do. That force is gravity, and within its domain, expansion simply does not win. Think about your own body for a moment. The atoms in your hand are not drifting apart. The molecules in your coffee cup are not slowly separating. The Earth is not measurably growing. The Milky Way is not inflating from the inside. None of these things are expanding, even though the universe around them is. The reason is straightforward. Gravity, at these scales, is so overwhelmingly stronger than the expansion pressure that expansion has no detectable effect whatsoever. It is not that expansion is paused within these structures. It is that gravity's grip is so tight that expansion cannot get any purchase at all. The math gives expansion an effective push of essentially zero at the scale of a solar system or a galaxy. Gravity has already won those territories completely, and there is no competition left to have. This holds all the way up the scale. Star clusters are gravitationally bound. Galaxies are gravitationally bound. The local group, that collection of roughly 80 galaxies, including the Milky Way and Andromeda, is gravitationally bound. So is the Virgo cluster, a far larger collection sitting about 65 million light-years away. Within these structures, member galaxies are not retreating from each other on the expansion of space. They are orbiting each other, falling toward each other, sometimes colliding. Andromeda is actually approaching us right now, closing the distance between our two galaxies at roughly 70 miles per second. The two galaxies are expected to begin merging in about 4.5 billion years. Expansion is not slowing that collision. Gravity is calling the shots entirely inside the local group, and expansion does not get a vote. So where does expansion actually take over? The threshold sits somewhere around the scale of galaxy superclusters. These are the largest gravitationally coherent structures in the universe, sprawling collections of galaxy clusters spanning hundreds of millions of light years. Even at this scale, gravity can sometimes hold things together, but push past the supercluster scale into the enormous voids between them, and the balance shifts. At those distances, matter is too spread out, too thin, too far apart for gravity to reach back and hold anything in place. Expansion takes over. The void grows. The clusters on opposite sides of that void are carried apart, not because either one is moving, but because the space between them is being added to, continuously, without any gravitational counterweight strong enough to stop it. This is the fundamental dividing line. Gravity wins locally. Expansion wins globally. Where local structures are dense enough to hold together, they hold. Where the density drops below the threshold, gravity needs to dominate. Expansion runs the show, and it runs it without interruption. The universe is not a uniformly expanding thing at every scale. It is a collection of gravitationally locked islands sitting in a sea of expansion that operates entirely in the spaces between them. Here is an analogy that gets at this fairly well. Imagine a chain of harbour towns along a coastline. Each harbour has boats moored inside it, tied to the docks, anchored to the seafloor, held in place by ropes and chains and the mechanics of the harbour itself. Outside the harbours, the open ocean stretches between them. Now imagine that ocean begins to grow. Not waves, not currents, but the actual volume of water between the harbours increasing. The ocean getting wider and wider over time. The boats inside each harbour do not move. The harbour walls keep them in place. The harbour itself is not being stretched. But the distance between one harbour and the next grows enormously. What was once a day's sail between them becomes a week, then a month. Then, eventually, the harbours are so far apart that no ship could cross the open water, no matter how fast it sailed. The harbours are fine. The harbours still have all their boats. It is the ocean between them that has become uncrossable. The universe works this way at every relevant scale. The Milky Way is a harbour. The local group is a harbour. The Virgo cluster is a harbour. They hold together, bound by gravity, immune to the expansion churning through the voids between them. But those voids grow. The distances between clusters stretch. What was reachable becomes unreachable, not because anything moved away through space, but because space itself piled up between the structures that gravity protects. The bound systems stay intact indefinitely. They will not be shredded by expansion. They will simply drift farther apart from each other, each one an island, each one carrying its gravitationally locked contents into a future where the distances between islands have grown too vast to matter. The harbours survive, each island of gravity holding its own against the growing ocean, but the ocean between them grows in a way that nothing can cross. Step back from the numbers and the horizons and the event boundaries, and you are left with a picture that is both enormous and oddly intimate. The observable universe is not a window. It is a museum. Everything you can see is a record of something that happened somewhere else, at some other time, in a cosmos that has already moved on. The reachable universe is smaller, much smaller, a fraction of what your eye can gather on a clear night. Most of it is gone, not destroyed, not dark, just gone from reach. The light still travels, the galaxies still burn, but the space between us and them is growing faster than any signal can cross it. And that gap is not closing. It will never close. 94% of what we can observe sits in territory that is permanently, physically, mathematically beyond us. Not because we lack the technology, not because we haven't been clever enough, because the universe is shaped in a way that makes most of itself unreachable by design. Here is the part that carries real weight. We caught it early. Humanity arrived at a moment in cosmic history when the universe was more connected than it will ever be again. Dark energy has been accelerating expansion for billions of years, and it will keep accelerating. The event horizon is not growing outward to include more of the universe, it is shrinking. The fraction of the cosmos we could theoretically reach with a light-speed ship is smaller today than it was 1 billion years ago, and it will be smaller still 1 billion years from now. Future civilizations, if they exist, will inherit a universe with fewer options. They will look out at a sky with fewer galaxies visible, fewer signals arriving, less evidence that anything exists beyond their own gravitational neighborhood. We are not living at the end of something. We are living at the most connected moment our position in the universe will ever allow. That is not a small thing. What does it mean to understand the shape of a universe you can never fully explore? It means something. Astronomers did not need to travel 46 billion light years to map the observable universe. They needed patience, mathematics, and instruments precise enough to read the color of ancient light. Redshift told them how far. The cosmic microwave background told them when. Type Ia supernovae told them the expansion was accelerating. None of that required leaving Earth. All of it required understanding what the light was saying. The unreachable is not nothing. It is the majority of everything. 2 trillion galaxies sit inside the observable sphere. 94% of them are beyond the event horizon, beyond any possibility of contact, beyond any hope of influence. But we know they are there. We have measured them. We have studied their spectra, counted their stars, estimated their masses. The fact that we cannot touch them does not make them absent from our understanding. It makes our understanding more remarkable, not less. Tonight you can look up and find the faint smear of the Andromeda galaxy with your naked eye. That light left before our species existed. In the deep field images from Webb, you can see galaxies whose light set out before Earth formed, before the sun ignited, before the solar system was anything more than a cloud of gas collapsing under its own gravity. That light has journeyed through the cosmos for more than 13 billion years. It crossed the event horizon of every civilization that never existed, every planet that never formed, every telescope that was never built, and it arrived here, now, at this specific moment in the history of one species on one rocky planet that happened to look up. The universe's inaccessibility is not a failure of physics or a limitation of human ambition. It is the shape of reality. Space expands. Light has a speed. Expansion at large distances exceeds that speed. The math is not cruel. It is simply what it is. Understanding it took centuries of careful observation, arguments, revisions, and instruments that would have seemed like magic to the astronomers who first noticed that distant galaxies were fading to red. The shape of reality turned out to be stranger than anyone predicted, and we found it anyway. The light still comes, from places you will never go, from things that may no longer exist, crossing distances that no speed can close, and somehow, every clear night, it still reaches you.